Let's begin lecture 4. So we have been looking at multi-planet extrasolar planets. So we will complete that discussion and then move on to some other things. Uh, so we know that there are more than 7,000 extrasolar planets that have been discovered so far. And out of these, about 800 sit in what are called multi-planet systems. Okay? Which means there's more than one planet. Of course, with the transit technique, it's easy. You find one transit, you calculate the orbit, you expect another transit at a certain time, but at some different time a transit happens, you realize it's a second planet, third planet, and so on. Can you also do it with the radial velocity technique? Find multiple planets? Yeah? There won't be a regular. So what will it be? What will it be in general? Suppose there's circular motion happening. Okay? Uniform circular motion is happening over the planet. Then the wobble will be like an SHM. Okay? The radial velocity will be an SHM. And if there are multiple planets, what will happen to the velocity? Radial velocity. Sorry? Yeah, it will be the superposition of the velocities that are produced by each of them. Of course, they won't be in phase, so it won't. There will be, you will have to model it as a sum of multiple SHMs with different amplitudes, different periods, and different phases. So of course, it's trickier to do, but it can be done because there are machines that observe the radial velocity variations continuously. So you are sampling the entire phase distribution of the velocities. And you can do that kind of modeling. So the radial velocity technique can also be used to do this kind of thing. It is a little bit subject to mass. See, remember, radial velocity technique is sensitive to both the distance of the planet from the primary, and it's also very sensitive to the mass of the planet. Okay? Whereas the transit technique is basically sensitive to the radius of the planet relative to the parent star. Both of them are sensitive to the Sinai factor. So if it is face on, there's no radial velocity and there's no transit. Okay. Whereas if it's like exactly edge on, you'll see transits and you'll also see very high maximal values of Sinai. Therefore, you'll see nice radial velocity variations. So these multiplanetary systems have been discovered. They provide insights into planetary formation and evolution. So how planetary systems like our solar system, how they might be forming, they provide a lot of insights. Often show compact orbital configurations, and this is because of our selection bias. We are sensitive to things that vary, transits which happen frequently. We are also sensitive to high amplitudes of the radial velocity. So we cannot see very distant planets, small planets, and so on. Exhibit orbital resonances and dynamical interactions. So frequently in this very compact space, the planets are so close to the parent star that they could often be tidally locked, like we saw in the example yesterday. But they could also be interacting with the star and with the other planets. The planets are very close. So for example, if Jupiter were as close as Mars, for example, it would have had a much bigger impact on the moon and on the Earth than it does now. So these kind of dynamical interactions are also quite frequent. This kind. So a few notable multi-planet systems. So TRAPPIST-1 is the most famous thing because there are 7 planets there, okay? And they're all seem to be quite small, Earth-sized, okay? And 3 in the habitable zone. So it's like really a fantastic laboratory. Kepler 90 has 8 planets that mirrors our solar system. Then there is HD 10180. HD is a designation that you will frequently see with stars. Okay, so that's just a number in some catalog. I've forgotten what HD stands for exactly, but you will HD some long number after that refers just to the designation of a star. Gliese 581, 3 confirmed planets, potentially habitable. And of course, this list will continue to grow. This is just what we have at the moment. So now what are these Earth-like planets? We saw this super Earths and terrestrial and so on. So now there is a narrower definition of Earth-like planets, which is this range of radii. So a narrower, very close to the Earth radius. This range of masses, primarily rocky, within the habitable zone of the parent star. And it should have an atmosphere, preferably with some biomarkers. So what are these biomarkers, etc.? We'll look at that in a moment. So if you ask like what are the places where you already have Earth-like candidates discovered? So the nearest star is Proxima Centauri to us. It's about just over a parsec or about 4.2 light years away. And this is the nearest known exoplanet. So this already is good news, is that we start looking and the next nearest star, we find a planet. Okay. So Proxima Centauri B is the designation of the planet, like Fomalhaut B was the planet of Fomalhaut. TRAPPIST-1e, similar size to Earth, potentially habitable. This looks promising. Kepler 442b, super Earth in its star's habitable zone. And this TOI 700d, first Earth-sized habitable zone found by TESS. TESS is that other observatory after that succeeded Kepler. Okay. So challenges in determining these Earth-like planets. It's not an easy game. This is now hard. It reaches the detection limits of current technologies. Okay. And then confirming the planetary mass and composition is quite hard. And yesterday we were talking about, we only determine the radius using the transit technique. Can we determine its mass? So one way which was suggested was you try to determine the mass using the radial velocity technique. Okay. So here, that can be done. But there are also correlations between mass and radius that have been observed. So you don't have to measure the mass of every single planet that you see transiting. You measure a mass of, say, 500 planets using the radial velocity technique, and you plot the correlation. And when you plot the correlation, if you see a good correlation, that means the density variation is not very high. You do see, you can measure the mass indirectly via this correlation, which has been observed. So one has to characterize the atmospheres of these small rocky planets. That, of course, is quite difficult and to do, and therefore cannot be done on a very large number of planets. And then one has to, through modeling, one has to determine the surface conditions and potential habitability. So all of this will be done in the future. Some of it is already started to happen, like with the James Webb Space Telescope. It's now operational, capable of detailed atmospheric calibration. So yesterday, after showing you that JWST atmosphere absorption curve, I went and read that paper and some critiques of that paper also. So it seems that there are still some degeneracies in the sense that either there are degeneracies between temperature and chemical composition and things like that. So we may not be, not everybody is convinced that we have found water and carbon dioxide in this planet. Okay. Also, of course, is very recent results. So one has to wait for confirmation and things like that. But it's a work in progress. So that's why. So although this is already in place, the results that it is producing still need to be confirmed and ratified. Planetary transits and oscillations of stars. Plato. This is a mission from ESA. It will launch in 2026. And the goal is again focused on these Earth-sized planets. Habitable Worlds Observatory. This is a very, very ambitious NASA mission. It's still proposed. So they don't even have a full design or anything. So this will take 20 years to come to fruition. And even this is also at the proposed stage. Okay, so idea is that large ultraviolet optical infrared surveyor. So you have a single telescope that can point to a star and try to obtain images in all these bands. And things look quite different. For example, in the infrared, if you go into the mid-infrared, then a planet like Jupiter will brighten up quite a lot. Whereas a planet like the star like the sun will fade considerably. So the contrast between, right now the star is infinitely brighter than the planet. But if the star becomes fainter and the planet becomes brighter, then it becomes slightly easier to detect, which is what happens with this kind of instrument. Again, proposed may take 10 years, 20 years. It may be scrapped in the future. So no promises. Okay. But there are also some advances, not in just building dedicated telescopes for extrasolar planets. Advanced detection techniques have also been developed. So the direct imaging improvements. So in direct imaging, as we saw in the case of Fomalhaut, the idea is to put something which hides the parent star. Okay, and that's called a stop. That device is then called as a coronagraph. And coronagraphs and star shades for better contrast. And these will be used in the Roman Space Telescope. So that Roman Space Telescope, due to launch, I think in 2027, is a very interesting idea. So the Hubble Space Telescope was there. So the military had US military had a spare mirror of the same size, which they no longer needed. Okay. So people said, okay, let us take that mirror and construct a telescope with instruments, construct a telescope with a very wide field of view, and we'll put corresponding instruments at its back end and observe. So this is a telescope just like Hubble, except that its field of view is much, much larger than what Hubble can observe. So that is a very interesting telescope, will be used extensively for direct imaging of stars, possibly for transits also. Extreme precision radial velocity. So right now we are doing radial velocity, as I told you yesterday, of the order of a meter per second. But if you can do 10 times better, then you will be able to detect Earth-sized planets using the radial velocity technique. So there are efforts underway to develop the technology for doing this. Improve long and short cadence. So right now, only a few stars can be observed if you are doing it all over the sky. Even if you are doing it with something like Kepler, its sensitivity is such that it can only detect planets up to a certain depth. So what you will want is a survey that can do the whole sky and very sensitively. So that Rubin LSST survey, which I briefly mentioned yesterday, starting next year, that is going to monitor 1 billion stars for 10 years. So again, it's not going to find something that could not be found with other telescopes, but because it is going to cover nearly half the sky, it's going to find many, many thousands of planets. many of them quite similar to the ones that we have found already with other dedicated instruments. But the numbers will shoot up so much that we'll be able to do statistics very effectively. Okay. The search for biosignatures is another area where things are moving fast. So the goal is to look for atmospheric biomarkers. And the idea is that oxygen, methane, and nitrous oxide are three compounds, or elements and compounds in this case, three chemicals which indicate the presence of life. Oxygen is almost unambiguously connected with the presence of life because it's a very reactive element, as I told you. If oxygen is there in its free form, that means it is being continuously produced, which means a photosynthesis-like event is happening. Surface features can also be looked at. So what is that surface feature? How can you detect the surface feature of that tiny planet where you can't even resolve the star? So what you're looking for is what is called vegetation's red edge. So the reflectance of plant leaves changes drastically at 700 nanometers. So if you take an image just short of 700 nanometers and take an image in another filter longwards of 700 nanometers, then the flux level that you will observe will change drastically in cases where photosynthesis is happening. So if you have a planet which is full of whatever plants, photosynthesis with chlorophyll, then you will be able to detect it. Of course, again, these are all extremely challenging activities. People are even suggesting looking for signatures like artificial atmospheric pollutants. So, and light pollution. So there are some chemicals which are produced in our system which don't normally exist on normal planets. I'm not 100% sure, but I think sulfur dioxide or hydrogen sulfide and things like this, these don't naturally occur in detectable amounts. Light pollution is another thing. So how that will be detected? Of course, radio light pollution is easy to detect. You just point your radio telescope at the star, and if there's a planet going around and they're transmitting radio waves, we can pick up and we can observe that. Optical light pollution is harder. So in India, the only effort that I know about, and I think this is the only effort to actually try and do extrasolar planet detection is at PRL, the Physical Research Laboratory in Ahmedabad. And they have a 1.2 meter telescope at a place called Guru Shikhar Observatory at Mount Abu. And they have built a spectrograph called PARAS. It's an optical fiber-fed spectrograph that can measure the mass of planets orbiting stars. And it was developed way back in 2008. And the PRL uses PARAS to search for exoplanets using FG and K dwarfs using the radial velocity technique. And they have discovered several new exoplanets. They haven't discovered hundreds or thousands of them, primarily because this kind of technique has always been less efficient. The transit technique with space-based telescopes is infinitely more efficient. By the way, why is transit being done always with space-based telescopes? It hinders the amount of light, but you're looking at bright stars. It hinders something else. Yes, but there are many planets which are transiting often, so you can observe them transiting. What is the problem?
The atmosphere itself
Yes.
interferes with the spectrum.
We are not really observing in the transit technique. We just put one filter and we are observing. We are doing imaging. We are not doing spectroscopy. So what could it be? Sorry? No, it's not so complicated. We are not looking in UV, we are looking in optical. Huh? Pollution is there, but you're again looking at bright stars, so it doesn't matter. So you're on the right track, but the exact answer is that flux calibration is very hard because of the presence of the atmosphere. The atmosphere itself can absorb more by 2% right now, and 10 minutes later absorb by 3% more, and then decrease it to 1% more, whatever. Its transmittivity, or the amount of light that it sends down, that can change by a few percent up and down, even on very clear nights where there are no clouds. Of course, there are clouds, it can change by 100%. But even if there are no clouds in the sky, the atmosphere is not stable. And because it's not stable and varies by several percent, reliably measuring changes of 1%. Remember, Jupiter is going to introduce like a 1% change in the flux of the sun if it blocks it. So measuring a 1% change in the wake of random jumps of several percent is very, very difficult. So that is the reason nobody tries to do transits from the Earth. They do it from space. Okay. So this is just a summary. It's an interdisciplinary collaboration. So there is astronomy, there's planetary science, and then there is biology. So if you want to know more, I mean, this is a big site to waste time on, because what they have done is they have collected every possible data on every possible known planet. Okay, what is its period? What is its radius? What is its mass? What is the host star? This, that, and all of that data is available on this website, and you can make plots of anything versus anything you want. Okay, so for example, the date of discovery you can just plot as a function of, I mean, the number of planets discovered as a function of time. So all of these things can be done. And more recently, when I was preparing my course, I encountered this talk by Anjali Tripathi, and this is the URL. And as people may know, there is this IAU General Assembly. So the international body of astronomers is called the International Astronomical Union. It has members from many countries, almost all the countries of the world. Every 3 years, all of these people gather together for a very big 10-day, 12-day long conference. That conference is going on now. It was there last week, and it will end, I think, tomorrow. So several people have gone from NCRA, and I think IUCAA must also send some people. And for the first time ever, the proceedings of the IAU General Assembly are being broadcast on YouTube live. So this is part of that. So in part of that, they had organized a special session called an Evening with NASA, where they spoke about all the NASA missions and what they're doing. And this lady, Dr. Tripathi, she gave a talk on all their extrasolar planet search plans. It really is quite spectacular. And of course, many of the other talks, right now, you're probably not well equipped to understand the talks, but later on in 6 months, when you understand the jargon, you can watch this. It's really excellent. I don't know of any other field where the primary conference of the field is broadcast live for free to everyone, for everyone to see. Okay. So now we change gears a little bit, and I'm going to talk about something which is not in the syllabus, But I think you should know, because if you don't know these things, then understanding some of the other things becomes difficult. So I'm going to talk about the time and the coordinate system used in astronomy. But I'm not going to go into details, because your astronomical techniques 1 course that you will have in January, February next year, that course will cover all of these things in detail. So I'm just going to give you a flavor of things. It's going to be very shallow and superficial. So time. So just a bit about time, the kind of times that astronomers use. Local time is the time at your longitude. Okay, so you go out, put out a sundial, and you measure the time. So you measure local noon, local time of sunrise, local sunset. Obviously, it was discovered some centuries ago that this is a very inconvenient way of measuring time. If Pune time is different from Nagpur time, which is different from Kolkata time, it causes havoc. So they came up with the concept of standard time. So we have Indian standard time, which is defined, and the same time is used all over the country. Then they said, okay, we need some sort of common reference time for the whole world. So they came up with this idea of the Greenwich time. Okay, so Greenwich is a suburb of London. There is a Greenwich Observatory there, but used to be shut down now. And they said, okay, that we will designate as the 0 of longitude, and accordingly, everybody adjusts their times. So then astronomers said, okay, no, we need our own time. And they called it universal time. So now universal time is really very close to Greenwich time. Okay. It's almost, for all practical purposes, it's identical, but not quite, because it is a time scale that basically approximates the mean diurnal motion of the sun. Okay, so by your clock, from sunrise to sunrise, will it take exactly 24 hours? No. Why is that? Yes, the Earth also moves in its orbit. That's okay, but the solar time is defined in such a way that takes into account the fact that the Earth is moving. Huh?
Orbit itself is elliptical.
The orbit itself is elliptical. That's correct. And secondly, the axis is inclined. It is not perpendicular to the plane of the ecliptic. So for these reasons, you have to define a mean diurnal motion of the sun. So, okay, sometimes it goes faster, sometimes it goes slower, etc. But we will define a time such that sunrise to sunrise, what is the mean period, that we will call 24 hours. Mean solar time on the Greenwich meridian. In current usage, UT refers either to a time scale called UT1 or to a coordinated universal time called UTC. Okay. So now what is this? Why UT1 and UTC? Why can't you just call it UT? The reason for that is that UT1 is observationally determined by the apparent diurnal motions of celestial bodies and is affected by irregularities in the Earth's rate of rotation. So the Earth's rate of rotation is stable. Okay, largely for all practical purposes, stable, but there can be jerks where it can just slow down or speed up slightly, very, very slightly. Over the long term, it's slowing down. Why do you think it's slowing down? Over millions of years, the Earth's rotation is slowing down. Huh? Not due to its tilt. Huh? Because of the moon, yes. So what does the moon do? Yeah, it's tugging on the Earth, it's producing tides. So what is happening is that the energy of the system is being continuously lost because of it. It's being lost in this tidal process. So two things are happening. The Earth's rotation is slowing, and simultaneously the moon is moving further away. Of course, this is happening very, very slowly. So over millions of years, you can notice the effect. So this is that. UTC is an atomic time scale, which is just an atomic clock corrected for general relativistic effects, everything. So it doesn't even lose or gain fraction of a second, nothing happens. But it is maintained within 0.9 seconds of UT1 by the introduction of 1 second steps where necessary. And generally, leap seconds are added at the end of June or December, or occasionally they can be added at the end of any month. It is possible to have a negative leap second also, which means you just don't count 1 second, move directly. So that last minute will have 59 seconds, and then the next minute starts. So this is the concept of time that people use. So our time is, we always define our time as Indian Standard Time is UTC plus 5.5 hours. So we are always ahead of. So remember, this UT, etc., doesn't take into account all this daylight saving time and so on, right? Those things are not included. This is just stays the same. Okay. So this is the concept of sidereal day versus a solar day. So the Earth is here today on day 1. Day 2, it moves here. Of course, this angle is exaggerated. So it only moves by 1 degree, exaggerated for clarity. But now the spinning Earth, let us say, goes around once like this, 360 degrees. But it needs some extra time to line up with the sun once again. Okay. How much is that extra time? That extra time is approximately 4 minutes. And that is called as a solar day. Solar day is sunrise to sunrise. And whereas the time that the Earth needs to turn around itself once is what is called as a sidereal day. And that is approximately 23 hours, 56 minutes, something. And the solar day is 24 hours. Could the sidereal day have been longer than a solar day? Currently, it's about 4 minutes shorter, but is there any configuration by which you can have it longer? Yes, if the direction, see what, I mean, just calculate the angular momentum of this system and the angular momentum of the Earth. They're pointing in the same direction. But if they were pointing in opposite directions, then the sidereal day could have been longer than a solar day. But this may be related to the formation of the solar system. Solar system formed from some birth cloud, which had a certain angular momentum. So it was rotating in a certain direction. So all those fragmented pieces also picked that up and they kept on moving. And you can see this across the solar system, except for some very highly inclined planets. They're aligned. Similarly, for the moon, there is a sidereal concept of a sidereal month and a synodic month, right? So here the new moon is there. By the time next new moon occurs, this full rotation has sidereal month was completed when the moon was here. Now it has to travel an extra distance in order to come to the new moon. Okay. So again, here the direction of revolution and the direction of the rotation of the moon, everything is in the same direction. Remember, the moon is also tidally locked. Okay? The moon is tidally locked around the system. So this is the sun, moon going around, and that extra time that it needs gives you a synodic month. So the sidereal month is some 27 days and some hours, and synodic month is 29 days and some hours. So it needs approximately 2 months extra, to 2 days extra to line up with the sun once again. To give you the moon, most lunar calendars use the synodic month. So many Indian calendars, for example, they have a synodic month basis. Another thing that you will encounter in astronomy is the concept of a Julian day. So it's very tedious to keep track of days and then find intervals between days. So if you're observing, let's say, a transiting exosolar planet, you don't want to say, oh, this was happened on March 8th and that happened on March 17th at this time, etc. What you do is you do a Julian date, which is you start counting from some day and just increment the days. And this was the original starting point. Okay. Julian date starts at noon. And the reason for that is it's just easier to determine noon. It's very hard to determine midnight via some simple observation. Noon is when the shadow of a stick is the shortest. That's the noon at a particular place. Astronomers use a concept called modified Julian day. So astronomers, of course, now we have clocks and so on. We don't have to do it with sundials. So we said, okay, let's just do it at midnight. That's more convenient. So there is a modified Julian day, which starts at midnight. So it'll be a half day offset. And then they said, let's just do reduced Julian day. So they said, instead of taking this ancient point as the starting point of our counting, let us simply start counting in 1970 or something and just have that as the first day or 08 day and count from there. So this is also used. So MJD, RJD are some things that you will encounter in any paper, many papers that you read. Another major phenomenon that changes the coordinates of stars and galaxies in the sky is a phenomenon known as precession. Okay? So the Earth is rotating in this direction and the precession is happening in this direction. How long does it take to precess one full circle? 25,800 years. It's a very slow process. However, it goes through this circle on the sky has a very large size. The inclination angle is 23.5 degrees. So it's going to be 47 degrees in diameter, that circle. So it's very. Note the direction of precession. Is it like a precessing top? If you take a top, imagine the Earth is a top and you spin it, which direction will it precess? It will precess like this. Okay, this thing is precessing like this. Why do you think that's happening? What causes a top to precess? Gravity. Okay. And what is gravity trying to do if a top is moving like this? What is gravity trying to do? Is it trying to straighten the top or is it trying to topple it? It's trying to topple it. Okay. And that is why the direction of precession is determined. Here, the moon has an angular momentum and it is trying to align the angular momentum of the Earth with that of the ecliptic, actually. The moon is also along inclined, but what everything is trying to do, including the other planets, is trying to align the angular momentum vector to the angular momentum vector of the solar system as a whole, which is the ecliptic. And that is why it's trying to straighten it rather than make it fall. And therefore, the precession is in the opposite direction. And the impact of this is that the pole star changes. So these stars themselves are very distant. They don't change direction or etc. But every 25,800 years, we go around this whole circle. So right now, this is our pole star. Okay. But in 88,000, this particular star, it's in Draco, I think, and so on. So different stars. We are fortunate at the moment to have a fairly bright star as the pole star. Some other points in time, there will be no bright star near the pole because of Earth precession. Okay. One more concepts from coordinates now. If you imagine yourself standing over here, there is the north side, east side, south side, and west side, and you are observing, let's say, this particular star over here, then you can define an angle on the plane of the Earth, which is called azimuth. Okay. It is measured from the north as 0 and east as 90, south as 180, and so on. So eastwards. So you measure this angle, and then you will measure what is the altitude of the star in degrees above the horizon. So by specifying this angle and that angle, you can specify uniquely any direction in the sky. So then you can say that at this azimuth and at this altitude, this particular star is there. So when you instruct your telescope to point in a particular direction, you will simply say that, okay, point to this azimuth and point to this altitude. So this kind of coordinate system is called altizimuth coordinate system. So this is how the sun moves in the sky. Okay. So this is for any northern latitude in the northern hemisphere. If you're sitting like us, then on March 21st and September 22, the sun will rise precisely in the east and it will set precisely in the west. Okay. And the angle that it makes with the zenith on that day will be equal to the latitude of that place. So we are at about 18.5 degrees latitude. If you observe from us, then on that day, when it crosses this north-south line, which is called the meridian, when it crosses that north-south line, the sun will be 18.5 degrees below the zenith. Right. So on June 21st, the sun is here, it moves further north. In our case, because we are in the tropics, it is beyond the zenith. So it is somewhere there. So it intersects the meridian somewhere here. And in mid-winter or in peak winter, December 21st, that's the winter solstice. At that point, it is gone further south. And here now, by just looking at the length of these arcs, you can see why days are longer, why days are very short in winter time, and why they are longer in the summertime. Yeah. How do stars move in the sky? Do stars also rise in the east and set in the west? What do you think? Position of star, of course, but where it rises will depend. Okay, so suppose the star is here. Okay, right now it's here. Where will it be, say, 6 hours later? Huh? It's opposite to Earth's rotation. Yes, Earth is going west to east, so stars go from east to west like the sun, right? The only thing that stars don't do is that they don't move north and south. So if a particular star is rising over here, it will follow exactly this track and set over there. And every day it will do the same thing. It will rise at one point and set at the exact same point. Whereas the sun appears to move north and south because of the inclination of the Earth's axis. If that 23.5 degrees didn't exist, if that was zero, there would be no seasons. Every day the sun would ride exactly in the east, okay, and set in the west. But that doesn't happen. Okay. So now astronomers are ready to define their own coordinate system. Okay. So there's the Earth. You take the equator of the Earth and you stretch it to infinity, or you stretch it to some large radius. Okay. And that defines for you a circle. And that circle is called as the celestial equator. It's just a stretch of our regular equator. And so so this plane, this blue disk that you see, that is inclined to the apparent motion of the sun. So this is the position of the sun today, tomorrow. It goes around this yellow circle. And that yellow circle is known as the ecliptic. Okay? It's the apparent path of the sun in the sky as a function of time. So it travels along the ecliptic about 1 degree a day. Okay. Do you people know why there are 360 degrees in a circle? Not 400, not 100. Why this crazy figure like 360? Huh? Yeah, it's very close to the number of days in a year. So the sun moves by about 1 degree every day. So that's where it came from originally. At the peak winter, the sun is here on the ecliptic. At the vernal equinox, which occurs in March, it is here. On June 21st, summer solstice, it's here. And during the autumnal equinox, it's there. Yeah. So now this is another rendering of the same idea. Okay. So this is again your celestial equator. This is that previously yellow circle, which we call as the ecliptic. You can take the North Pole and stretch it out. That's called the North Celestial Pole. Similarly, South Celestial Pole. And then the equinoxes, etc., are marked as previously. So now this is a different rendering. So this is your, what do you think this circle represents? It's written there actually. That's the horizon. Okay. This is your South Celestial Pole. This is your North Celestial Pole. And this is how your Earth is rotating. So the stars appear to rotate in the opposite direction. So there are certain stars which are within this blue circle, which will never rise or never set. They're always visible in the sky. So in the northern hemisphere, our pole star is like that. You see it in December, you will see it. You see it in May, you will see it. You'll see it in any season, you'll see it at the same location. And of course, these other stars will keep going up and down as the sphere rotates. But simultaneously, there are some stars which never rise, which means you can never see them. So from our point of view, there are beautiful objects called the Magellanic Clouds, which are satellite galaxies of the Milky Way, which are quite easily seen from the southern hemisphere, which lie in this zone for us, and therefore they never rise. And as you go to higher and higher latitudes, more and more stars will become circumpolar, and more of the sky will never rise. And ultimately at the North Pole, you only see the Northern Hemisphere stars. You don't see anything in the Southern Hemisphere. The pole star is overhead and all stars are revolving like this. Nothing rises, nothing sets all through the year, same stars. So this is a picture of circumpolar stars. Just go there, open your camera shutter, keep it open for several hours, and the stars will trace these circular arcs. Okay, so now we come to the main thing that I want to define in the coordinate system, which is the system of right ascension and declination. So if you want to give the coordinates of a certain location on Earth, you give two numbers, the latitude and the longitude. Similarly, if you want to define the coordinates on the sky, okay, now these coordinates are defined irrespective of the Earth's rotation. So it's not like altitude and azimuth. Every star, every galaxy can be assigned a unique set of coordinates which define exactly where it is. So those two coordinates are called right ascension and declination. Let us look at declination first. That is quite easy to understand. So it is the exact analog of latitude that we have. So just like our latitude goes from 0 degrees to 90 degrees and then 0 to minus 90. Similarly, declination goes in that range. Right ascension is the analog of longitude, okay? And it goes from 0 degrees to 360 degrees, okay? It increases eastwards always. And just like you don't have to define the equator. Equator is self-defining. However, in the case of longitude, we said the Greenwich meridian will be the 0 of longitude. So similarly, you need to define a 0 of right ascension. And that is defined as what is called as the first point of Aries, denoted by this gamma symbol. And basically, it's the position of the sun on the date of the vernal equinox. So on March 21st, where is the sun sitting? That's your 0. And then you measure it 0 to 360 degrees. And this you measure from minus 90 to 90 degrees. RA is measured in hours, minutes, and seconds. Okay, so this is a little bit peculiar. Hours means that you will go from 0 hours to 24 hours, 360 degrees, and minutes and seconds. So, like for the subdivisions of arc, 60 minutes in an hour, 60 seconds in a minute. The declination is measured in degrees, minutes, and seconds. Here it's exactly like the arc second, arc minute kind of rule. Again, the same thing. But nowadays, people are saying this is just so inconvenient, specifying so many loose numbers, because anyway, humans are not reading those numbers and plotting them anywhere. It's computer programs which are doing it. So just put it as decimal degrees, both these things. So that is what is increasingly used in various catalogs, etc. That you will have the RA in decimal degrees and the DEC also in decimal degrees. So DEC will go from minus 90 to 90 and RA will go from 0 to 360. Okay, so we discussed a little bit about longer days, tidal friction and so on. So how much is the Earth slowing down? 2.3 milliseconds per century. That's the slowdown of the rotation. So how much longer before we have 48-hour days? You can do the calculation. Assuming the slowing goes down at the same period, it will take 3,800 million years for us to have 48-hour days. Where it will happen. I think this may be a good point to stop, because next we come back to a topic, magnitudes, which is definitely there in your syllabus. and I'm going to cover that. But I think I'll stop here, take any questions that you have, and next time we'll start with magnitudes. Yes. So that is the biblical date. So in the Bible, there is a date given for when God created the world. So there is that story of Genesis where they said that over 7 days the whole universe was created. So they have given a date. No, nothing exists for them. Anyway, I mean, it's just a reference date. You can choose Mahabharata war date if you want. It doesn't matter. But yeah, that was the Christian belief that the world was just created about 7,000 years ago. Less than 7,000 years. Earth has precession. The precession is caused by the fact that our orbit is inclined. Okay. And there is a angular momentum of the entire ecliptic. There's angular momentum of the Earth's own orbit. Okay. So what is this angle of rotation inclined to? It is inclined to the plane in which the Earth is orbiting the sun. So rotation is inclined by 23.5 degrees with respect to that. So now there is an angular momentum of the Earth going around the sun. Most of the other planets are also going around in almost the same plane in the same direction. So there is a net angular momentum for everything in the solar system, which is angular momentum vector perpendicular to the ecliptic. Okay, so there is a tendency, or there is a force which tries to straighten it and make the angular momentum vector align with the angular momentum vector of the ecliptic. And not just the Mars orbit is also inclined, that will also precess. Okay, Jupiter's orbit will also precess. So there is nothing special that only the Earth is precessing. Everything else that is rotating is precessing. But its tendency is opposite to that of what you observe on the top, because in the top, the gravity is trying to make the rotation like this, right? It's trying to topple the top. It is not trying to straighten it.
That angle with the center of the galaxy will incline with the whole solar system.
That is much more complicated. What happens in that case is that the entire solar system, sun basically, see, the sun carries the planets with it. So relative to the galaxy, if the sun goes somewhere, planets will accompany. They have no choice. So what's happening is that there is a plane of rotation, okay, of the sun around it, but it doesn't actually stay in that plane all the time. It does a sort of sinusoidal motion over and above and below that plane. So instead of staying in one plane, it actually, there are perturbations which take it upwards and downwards and upwards and downwards again. Of course, this takes a very long time. One rotation of the sun around the center of the galaxy takes around 200 million years. So it's a very slow process that happens over millions of years. And the reason for that is, I mean, you have to go into galactic dynamics to understand why that happens. And you'll go into that in your galaxies course, which is again January, February next year. Okay, so we'll stop